We're going to cover a case study of how to regress parameters from a first order plus dead time model. And just to review, we have our first order plus dead time model, which is tau p times dx dt equals negative x plus the gain kp times our input u as a function of t minus theta p. So our three parameters are kp, that is our gain, our time constant tau p, and that's basically how fast it gets to the new value, the new steady state value, and then our final parameter is theta p, and that is our dead time or the delay. And that is essentially when you make a change, it's how much time it takes before you start seeing the effect. Okay, so we have this data right here. I'll show you how to pull that into your Python script. We have a case study here where we have a pipeline, and the valve is right here. Here's the valve, but it's at this end of this very long multi-kilometer pipe, and the wellhead for oil and gas might be way over here, and you may have, for example, 15 miles or of pipeline there. And so when the well turns on, there are valves here at the wellhead as well, but when this turns on, it begins flowing. You have the subsea temperature, which is less than 4 degrees Celsius, and this whole pipeline is going to be very cold. Now you have hot reservoir fluid, oil and gas, fluid that's going to be coming in here, and that is going to travel the distance of the pipeline, and we're going to see that the fluid remains cold for a little while because the pipeline itself needs to heat up. And so here we have the pipeline, the flow turning on, and here on the bottom part is the temperature as it increases over multiple hours. So there is the data, and what we want to do is create a first order plus dead time model with this data and just see how well we can fit this response with just these three parameters. So let's go first of all to Python, and what we're going to do here is just go ahead and grab the data and be able to plot it. So first of all, I'm going to import pandas. Pandas is going to be a package I'll use for importing the data and just doing some simple analysis. Matplotlib is going to be for plotting the data. I'm also going to just download the data set with wget. Now by default, this is not installed in Anaconda or Python, so you might need to get it. I'll do import pip. I'll use pip.main to install wget, and then I'll import wget. Okay, now if you already have wget, then I'm going to indent this, and let me just do try import wget, and if I don't have it there, then import it, import pip, and install wget, and then import wget. So I just needed those two additional lines there, the import pip and the pip.main, to get that additional package. Okay, let's go and download the pipeline data with wget. Here's the URL for the pipeline data, and it's just going to download as pipeline underscore data.txt. You could even plug that into a web browser and grab it. But I'm just going to use wget in my script to get that. I'll download it with that URL, and then I'll rename the file to data.csv. So to do that, I'll have to use a shell utility and import move. And then I'll move the file name that I got to data.csv. And then I'm going to import this data with pandas. So I'll read CSV with this package pandas, which is shortened to PD. So pd.readcsv, and I'll read data.csv. And I'll have time and my valve, and this is just for labeling some of the X and Y labels. Okay, I'll go ahead and print some temperatures. I'll print TC, and this is the temperature, and I'll just print the first few rows of that temperature. I'm just going to print the data. This is going to be the column that corresponds to that name, temperature degrees Fahrenheit. And then I'm also going to print you know, the minutes as well. Okay, or sorry, this is the min and max. Sorry, this is the minimum of that data column and the max of that data column. So this is the temperature in degrees Celsius, and I just printed the min and the max over the whole column. And I did that with the min function and the max function, converted it to a string, and then printed it out as min and max. Okay, let's go ahead and just plot this. I'm going to create a new figure. I'll do a subplot. On the top, I'm going to do the valve data, you know, whether it's open or closed, do that as a blue dashed line. And then on my second subplot, I'll do my temperature and X label. This is going to be in hours. I converted all the times. I divided them by 60 because they're in minutes. I just wanted to see them in hours. Okay, so let's go and just run this. Okay, I'm going to go ahead and just open up this script. You can do this with Spider or Jupyter Notebook or with IDLE. I'm going to do IDLE here. Okay, and you can use any version of Python for this, Python 3.6 or above. This is just 2.7. So you can see there the valve position and the temperature. So it went and downloaded that file from the internet, and then we have a copy that is stored locally here. Let's just look at that data file. Here's the data file that we're dealing with. If you double click it, you have Excel. You can open it up with Excel and see those values. You can also just open it up with something like a Notepad++ and see the comma separated values there. Okay, so that's the data that we're pulling in for this example. Now what we want to do is we want to try to fit this to that first order plus dead time. I'll show you how to do this in Python. So this script is going to be a little bit long, but let me, I'll run through it, and then as I run through it, I'll also try to explain some of the things that we're doing here. Let me go ahead and just bring up the this as well, and then just as I go through it, hopefully be able to show you, you know, how to set up an optimization problem in Python. Okay. Resize this, just move it over to the side, and let's see if I can do that without resizing it onto there. Okay, so here I'll just make a little area for me to, okay, there's my model that I'm going to try to fit, and then just as I go through here, I'm going to need NumPy, I'll need Matplotlib, I'll need to have my ODE integrator, just be able to integrate that differential equation and then compare it with the measured values. I also need SciPy optimize. So we're going to minimize this function of the objective function that we're going to have is going to be to minimize, and then we'll sum up all of the points from the beginning to n-1, and then we'll take the measured value minus the model value, the predicted value, and we'll square those. So we're going to try to minimize the difference between the measured values. Okay, it's going to look something like that. And then the predicted values as well. Maybe I'm predicting like this. Okay, and at every point in there, I'm going to have a difference between those two. I'm going to take that difference and I'll just square it. So what I need to do is be able to, for different values of Kp, Tau p, and Theta p, I need to be able to calculate a new predicted trajectory, and I'll have my predicted are these x's right here, and then I'll have my data there as well. I need to be able to calculate the difference between those two, and then let the optimizer try to minimize that by adjusting those three parameters. Okay, so let's go on here. I'm also going to need to use the SciPy interpolate. You'll see that with my U value, my valve value. Okay, I need to be able to request any point in between the measured values. Okay, so here's my CSV file that I'm importing. I'm just going to load that data.csv file that I already grabbed before. And I'm going to skip the first row because it has a header in it. And then my delimiter is going to be a comma. So I'm just going to separate this out. This is going to be the U0 is going to be, that's going to be my initial value of the valve. My Y initial value is going to be just that very first row of data as well. And then I have my time vector. I'm just going to take the whole time and then subtract off the initial value. So just in case my time does not start at 0, I'm just going to force all of, just shift it back so that my time starts at 0. Okay, and then I'm just extracting my U value, that's my valve, and then my Y, and this is my measured value for Y, and that is going to be the third column of my data. Okay, now I need to specify the number of steps. It's just going to be the length of my time vector. And then I have my delta time as well. Okay, that's going to be the time step that I have for each time interval. And then I need to create the linear interpolation of U versus time so I can request a U at any continuous time between the beginning and the end, and it will give me an interpolation between any two measured points. Okay, so I'm going to use the interp1d to do that. Okay, I'm going to first of all go ahead and define my first order plus dead time approximation. This is going to be my FOPDT model. And I'm going to have some arguments. There's going to be Y and T in there as a standard, any standard ODE model. And then I have these 4 additional inputs, UF, KM, tau M, and theta M. Those are going to be my, UF is going to be my, my inputs that I'm going to have for my valve. Those are just known and fixed, but they could potentially change at any time point. And then I have my 3 parameters that I'm trying to find. So it's going to be my 3 optional arguments, and the optimizer is going to change those, and I want to be able to calculate a different model for each of them. Okay, so here I just wrote the description of those, and then I'm going to try, if t is less than theta m, then I'm just going to say that u equals 0. So that's a case where, if I'm not, my theta m says if my time delay is too much, I've got to make this approximation there. I'm just going to approximate it as 0 for now. And then accept. Okay, this is where I calculate my u value and my derivative. Okay, u equals u naught, and so I have my approximation there, my uf at 0 if my theta m is less than 0. Else, I'm going to use my linear interpolation there to find the correct u value with that time delay, and then there's my derivative that I'm returning. Okay, so there's basically my differential equation. One thing that you got to remember to do is here with this differential equation, you got to put everything except the derivative on the right hand side. So I'm just going to divide by tau p, basically move that over, and then you see that on line, the last line here on line 43. Okay, and then I'm going to return dy dt. Now I'm going to simulate my FOPDT model with those 3 unknown parameters. Here's my simulation. I have my, just going to break my x down into km, tau m, and theta m. Now I just limited the lower values of tau m and theta m to basically be 0, because if you have less than 0, it can have an error. That doesn't make sense for a time constant or delay to be less than 0. Okay, now I have my storage of my model values. I have my initial condition as well. This is just a standard differential equation integration. So I'm just going to kind of fly through this. There's my FOPDT model that I'm integrating. I'm going to loop through all the time steps with all of my inputs and be able to calculate this this new trajectory of values right here. Okay, so that's what I'm doing with this. I'm calculating each of those time points and just kind of stepping through that simulation. Now I have my model, and I need to now define my objective function. Okay, I'm going to simulate the model. I'm going to call the sim model with these 3 parameters km, tau m, and theta m that are all embedded into the x vector. I'm going to calculate my objective now. I'm going to penalize any constraint violations. So if tau m is less than 0, I'll just say, add some to the objective function to discourage that. And then I have my measurement error here. So this is the, you can see the model measured minus the model squared. And there you can see, and it can be model minus measured squared. And that's what I have right here is actually model ym minus yp. Okay, for each of those I values in those vectors. Okay, and let me just continue on here. Okay, now I return the result, which is my objective value. So that's what the optimizer needs. It needs to, for each of those 3 guess values, it needs to be able to guess values and then return an objective function from this function, from this objective function. And then I'm going to give it some initial guesses. I'll just say that my guesses are going to be zeros, and I'll change those. I'll say my gain. In this case, I'll say, just looking at the graph, let's just go ahead and come up with some initial guesses right here. This is a delta U and a delta Y. And my gain is going to approximately be equal to delta Y over delta U. And so that looks to be about 50 divided by 100. So that's about 0.5. So just graphically, I saw that was about 0.5. My time constant, now my data is coming in minutes, but my model is, and then I'm graphing it in hours here. So I look at about where it gets to about 63% of the way there. Okay, and this time right here looks to be about, I'll just guess 5 hours or so. It's probably a little bit less than that, but I'll just guess 5 hours just as an initial guess. I'll let the optimizer improve that guess. Okay, and then my delay looks pretty negligible. I'll just add in 0.2 minutes just to give something for the optimizer to start with. Okay, now I want to show my initial objective value. I'll just call that objective function with my 3 guess values. Okay, and then I'm going to optimize. So this minimize function is then going to take my objective function and my initial guesses and then return a solution that's hopefully better. And then another way to solve this is with bounds on variables. So if you want to use the method SLSQP, I kind of have mixed results with that, but there I just commented it out to show that you can add some bounds on your variables. Let's say your gain is going to, it's going to be between 0.4 and 0.6, and your time constant is going to be between 1 and 10, and then your delay, your dead time is going to be between 0 and 30. You could add those in if you wanted to. I just didn't have very good luck with that. Okay, I got my x values out, my new parameters, kp, tau p, and theta p, and then I'll show my final objective as well with plugging in the x values instead of the x naught values. Now I also have, just breaking those out into kp, tau p, and theta p. I'm just going to print those 3 individually. And then let's just go and calculate the model with the updated parameters. There's ym1 and ym2. So I'm just going to calculate both of those and then just plot my initial guess versus my final solution, and I'll plot it. Okay, so here's my measured data, my initial guess, and then my optimized, and then I'll have my output and my legend, and then I'll have my second subplot with my u values showing the interpolation and the measured values. Okay, so there is my there's my script. It's a little bit complicated, these functions in there, but hopefully you kind of understand what is going on with that script. And I'll go ahead and run this. Okay. So it has this initial steady state objective. So that is the sum of all the squared errors. and then hopefully when it's done it'll have a better sum of squared errors. It's trying to minimize that objective function, and it's just going to take a little bit because it's integrating this over and over and over again with different, kp, tau p, and theta p values. This one's actually using the Nelder-Mead method, which is kind of a slow optimization method. There's better gradient-based algorithms that are out there that, and if I may post another solution that shows one of those gradient-based approaches. You can also use something like Microsoft Excel. I think I showed that in, so while this is calculating, let me just show that. This is the assignment right here where we're doing the parameter regression. Okay, and so it has some of this additional information with just the starting script. I'll post a solution here below this video there below. And then in case you missed some of the things about the graphical method for fitting this, here are the 7 steps to fit an FOPDT model just graphically. Now sometimes we don't have this nice step input, so we have to use an optimization method like we're doing right now. But let's there's also some additional information just on FOPDT optimization fit, and there's a script here. Well, there's the Excel example of fitting FOPDT to data with Excel, and then if you scroll down just a little bit more, you'll see a script here that's very similar to the one that we just discussed. So you can always take this and then modify it for your case if you want. Just click the down here in the bottom right, click the get code. Don't just copy that directly, because it's gonna it will likely cause you problems with the formatting and stuff. Okay, so it looks like it just finished. So there we have our process data, which are the little black X's, and then we saw our initial guess as well. So that's what we had initially plugged in with a gain of 0.5, time constant of 5 hours, and then a the delay basically negligible. So that was our blue line that we just came up just from doing the graphical fit, and then the optimizer improved that further, so you can see the red line in front of the black X's. So I'm going to go here and just take a look at those values. Kp is about 0.41. The tau p is 212.8 minutes. So so 5 minutes. Let's see, that would have been about 300, or sorry, 5 hours would have been about 300 minutes. So it would reduce that a little bit as well as the gain. And it looks like the dead time there was essentially negligible. So that means as soon as the valve opens, there's essentially almost an immediate response from that sensor. Okay, so that is it for these two. I hope you learned something about parameter regression here. We're going to use optimization solvers to minimize, in this case, a sum of squared errors.